for giving me the opportunity to speak here in this great venue. So before I start my talk, I would like to use this opportunity to advertise, say, my baby, this big machine learning course at Aalto, which is now offered fully online. So we are still happy to get some more students via Open University. If you're interested, the first lecture is next week, Tuesday. Okay. So my talk is about this slogan, artificial intelligence is the new electricity. How many of you have heard this slogan? Okay, so quite many. It's I think was made popular by one of the big players in machine learning and AI, Professor Andrew Jung from Stanford. However, their understanding of this slogan is still quite vague. So I will try to dig a bit deeper and try to make this analogy more precise. And to this end, what comes at my disposal, I've been trained as an electrical engineer. So I did my PhD in TU Vienna within electrical engineering, where I learned how to design power grids, how to distribute electrical power or electrical energy. And I learned also a long time ago how to design electrical engines, which turn electric power into other forms of energy. And now I became, since 2015, assistant professor for machine learning. So now I'm working on this new electricity and trying to apply my knowledge and the models that I learned a long time ago on how to distribute electricity for distributing knowledge or intelligence. Okay, yeah, about my research, I'm heading the group Machine Learning for Big Data. We have currently 5 PhD students, several master and bachelor students. And what we do, basically, we consider 2 questions. The first one, when is machine learning possible at all in a given application? When does it make sense to try out all these fancy tools, deep learning tools? And if it is possible, how? So what are efficient algorithms for machine learning, for doing machine learning, for kind of turning this new electricity into something else, like kind of success of a business? Yeah, as I mentioned, I'm also quite active in teaching. I teach now this big course on machine learning, maybe now the largest course on machine learning in Finland. This year we expect 700 students at least, maybe now a bit more, I hope. I also teach convex optimization. This is one of the main tools, or one of the main kind of machines that turn this new electricity into knowledge, convex optimization methods. And I also teach an artificial intelligence course. Okay, so let's jump into the fray with looking at how electricity fuels modern society. Still we are, let's say, fully dependent on electricity. Everything here, almost everything here in this room is powered by electricity. So why is electricity so convenient? What makes it so extremely convenient, electricity?
It's fast.
It's fast. Any other ideas? Yeah.
It's readily available.
Readily available, yeah. We can generate it, and we can also distribute it efficiently. Okay, so this is how electricity fuels the modern society. And then there's this analogous picture for modern AI. What is the fuel for modern AI? The fuel is the data. We have a lot of data, AI to take off. So in some settings, it's kind of already AI has surpassed. I didn't know the name of the movie. I just knew something about the plot, like it was about a husband whose wife has been kidnapped, but the husband didn't want her back. And I googled this and it digged it out. It was a movie from the 80s with Danny DeVito. It's incredible how this AI works in certain applications. Also, what I really find impressive, Shazam. How many of you know Shazam? Okay, quite a few. So I was always eager to know if I hear a sound, to know what it is. And then I watched one of my favorite movies. When you're in the mood of revenge, sometimes you are, you watch Kill Bill. And there's this fighting scene. And did you recognize there was a song in the background? There was a song in the background playing. Does anybody of you know the title of the song? How many of you have watched Kill Bill? Nobody of you knows the song. Sorry?
Don't remember.
Don't remember. Did anybody ever knew it, what the song is? Yes?
Yeah, but I don't remember the.
Okay, yeah, it's the human binds nobody but me. I had no chance to find it out in regular ways, looking up a lot of pages, soundtrack lists. Then I remembered there's this thing called Shazam on my smartphone. This is something like digging out song titles, and I tried it out, and it digged out the title in seconds. So basically, the idea behind Shazam was published already 2003 in a paper called An Industrial Strength Audio Search Algorithm. And what is kind of remarkable here, what I will touch upon later, it is based on networks, on using fast Fourier transform, which is based on a network representation of computing spectrum, and on fast search over trees, for example, binary tree search. Yeah, so this kind of gives a bit background now for looking at these questions. How can we make electrical engineering for AI? How can I, as a trained electrical engineer, make a contribution in AI? So I'm naturally led to think about, so what is this analogy? How do we generate this new electricity? How do we turn raw data, which is the kind of the source of energy, into power that we can distribute? And then, of course, how do we efficiently distribute this new electricity? And what are the appliances? What are the machines that turn this new electricity into something else that we would like to have, like insights for business decisions? And what we currently look at, we look at network models. So this is a key pattern in modern AI systems. They use networks not only to organize data, as mentioned here, but also to organize computation. So does anybody of you know a computational model that is based on networks? What methods are based on organizing computation in networks? Graphs? Yeah, networks, artificial neural networks are nothing else than organizing computations as networks. Like this here, like the fast Fourier transform organizes a computation here from the time signal to the Fourier coefficients as a network. That's nothing else what the deep neural network does. It organizes the computation of a predictor from input features to predicted labels at the output in the form of a network. Okay. What is different in artificial neural network, that we have weights. Each edge in an artificial neural network has weights which we can tune or adapt. And that's then called learning, deep learning, adapting the weights of an artificial neural network such that the overall map from features to output yields good results or small training error. Yeah, so this is kind of our underlying theme at the moment in our research. We look at network models. And on the very low level of network models. So these network models pop up very natural in many applications like social networks. So each user in a social network is a node in a network, and the links in the network are friendship relations. Okay? Friendship in the sense of Facebook friendship. In bioinformatics, biology, we have molecules which are kind of organized as a network structure of constituent atoms. And also I digged out a very cool example, the universe. In particle physics, the universe is a network. The nodes in the network are events in space-time, and these events are kind of connected by particles which traverse from one node, one event in space-time to another event in space-time. And what particle physicists do, they sample a network. They try out particular relations between events and particles, for example, in CERN. So what we do, instead of representing the data as what you normally do, you represent data using features, real valued features. So this is this prime example of Andrew Yang in his machine learning class, predicting house prices based on the area, living area. So the input is represented by a real number, living area, and you want to find out a mapping to output the price. And then the question is, why do we embed the input features into the real numbers? The real numbers is way bigger than the set of numbers that we have here. So a more economic way to represent the input data, we just take the input data points and say these are our features. So for each house, we have one node. Okay? One data point is one node in a graph. And I've shown here a map of Helsinki. So we have certain houses in different areas. And if they are similar in similar areas, we connect them by edges. And the amount of similarity, if they are very close or very similar, have the same number of floors. Both houses have an elevator, so they are very similar. Then we have here a large weight. So we also indicate the amount of similarity by a weight. And for some nodes, we know the label. So for some nodes, we know what the price would be. Okay. So these labels are denoted X, Xi for the ith node. And in machine learning, what we're interested in many machine learning methods, find out what the labels are of those data points where we don't know the labels a priori. Because getting labels, the label is kind of the value or the insights in this information or in the raw data which we're interested in. The labels are kind of the answers to our questions. Should we invest in this or in that more? And finding out labels typically is costly. Costs human labor, or for example in marine biology, means to send out a vessel with marine biologists to the Baltic Sea for a week. Or in particle physics, acquiring labels means running a CERN experiment. Or might cause deaths. So getting along with only very few labels might save lives. Yeah, and there's this mechanical Turk. How many of you know the mechanical Turk? So you can buy labeling workforce. If you have kind of your application is to find out if a certain image shows a cat. So the label of a data point is either cat or no cat. And you have a hard disk full of images. And you want to know are these what images show a cat or no cat. Then you can upload your data set to Mechanical Turk. And this is then distributed to workers all over the world. You pay for a certain amount of work and get back the labels. Human labeling or labeling costs money. So we typically only have very few labels available. And we need to exploit the structure in the data to get by only with very few labels. So we only might know here a label and here the label. In this case, the label means the house price. So this kind of generates the electricity. So the labels, the known labels, are the generators of this AI electricity. And now we have to distribute this AI electricity. So how do we find out the labels for all other data points? Any ideas? Intuitively. So we know the house price here and the house price here. Can we say something about the house price here of this node? Yeah.
It's probably more close to the J price than the I
yes.
price.
So this notion of similarity is underlying many machine learning methods, if not all machine learning methods. And in our case, we call it the clustering hypothesis. The clustering hypothesis means that the labels of well-connected nodes of clusters are similar. So this is corresponds that if you're in a group, a Facebook group or Facebook cluster of friends which are very close connected to each other, then you typically have the same age. So the properties you have or the labels of these data points are similar. And we can quantify this hypothesis using a notion of total variation. Okay? So what we then do is quite simple. We learn the labels by minimizing a sum of two components. So the first component kind of requires the labels that we learn or infer to kind of agree with the initial labels, so with the human opinions on a few data points. Or we had here in this house price prediction problem, for 2 nodes, we had an expert from a bank. Banks often have experts which are very good in quantifying prices or kind of how much a house or a flat is worth. Okay, for these 2 data points, we know the label. So what we then require, whatever our algorithm outputs, it should agree with the initial labels, with the human expert knowledge. But on the same time, we have a second component which requires the labels to be clustered. So the labels of well-connected nodes are similar. So we end up with this kind of empirical risk minimization problem. And that's quite also a standard formulation of machine learning problems. A machine learning problem, in the end, is nothing than an optimization problem. You want to find a labeling or a predictor of the labels such that the empirical risk or the disagreement with the available information is small, but at the same time also this predictor satisfies some regularity, or in this case is clustered. Any questions up to here?
So how does that kind of graph, you had the one slide with the map. So yeah, how does this kind of work? Doesn't it kind of overfit the like geographic location or something like this? Because
so we in our work currently assume, we make our life easy, we assume that this graph structure is given. But finding out an accurate graph structure representing data is not trivial. So you typically have some domain knowledge, like in this area. This is kind of the campus area of Aalto in Otaniemi.
yeah.
You have some similarity in the house market,
Yeah.
or the prices. However, we also look at methods that learn this network structure based on correlations in the data. So it looks at a lot of historic data sets and finds these edges here by spotting correlations in the data. This is then called probabilistic graphical model selection. Yeah. So this might be non-trivial to get the graph structure. But for the time being, we assume somebody provided us with this. And in some applications, it's pretty natural, like in social networks. You can use the friendship relations, or in time series data, you have kind of these consecutive time steps, which form a chain. Or an image like this here, the pixels, each individual pixel is a data point, and they are connected to the nearest neighbors, which gives rise to a grid graph. So images you can characterize well, in general, using grid graphs. Okay. Any other questions? Okay, so we came up with this formulation. And then there are 2 questions which relate to our basic research questions, guiding questions. When is machine learning possible, and how is machine learning possible? So when is machine learning possible means, in this case, when is the solution of this problem any good? When is the solution of this optimization problem a predictor or a labeling that is reasonable? And for this, to study this, we need to understand the characteristics of this optimization problem. And what we found out is that the quality of the solutions of this optimization problem depends on the connectivity of the nodes, which we call sampled nodes. So for the sampled nodes, we know the initial labels. And if those nodes are well connected, so via strong links, to boundaries between, or to boundaries between clusters, then it works. And we make this notion precise, or we make this condition precise using the notion of network flows. So how many of you have worked with flows over networks? Quite so. So this condition amounts to the existence of a certain, a sufficiently large flow from the sampled nodes from one sampled node to the other sampled nodes via the edges in the empirical graph. So we interpret this this data graph, these links, as water pipes, which can carry a certain amount of water or fluid or of electricity. And the amount of electricity or fluid depends on the similarity between the data points. So we interpret these similarity weights, which I mentioned here. So we equip each edge with also a number which expresses the amount of similarity. And in our approach, we interpret this weight as a capacity constraint. And using these capacity constraints, we have to ensure that a sufficiently large flow can exist between sampled nodes via the border edges. And this we call a network compatibility condition or network null space property, which are closely related and essentially amount to the existence of certain network flows. So we characterize the flow of this new information via this network null space property. And if this is satisfied, so if there's a sufficiently large flow possible, then the solution of this problem is accurate. It's an accurate recovery or an accurate learning method. The labels that you get out of this problem are accurate. Okay. Yes?
Sorry, did you mention that already, but how do you define the sufficient amount of data then?
The sufficient amount depends on the weights. So the weights, each edge here has a weight, which is the similarity weight, and the amount of flow is related to the value range of these weights. So it's more or less proportional to the weight of the boundary edges. Those dictate the amount of flow that has to be possible between the sampled nodes. So if the boundary edge has a weight 2, then the amount of flow has to be proportional to 2, or like 2 in this case. If the edge has weight 10, then the flow has to be at least 10. So it's related to the weights in this data network.
So do you have to save the data that you get from these edges somewhere so you can evaluate it later?
I assume that these weights are given, are specified. There's some domain expert which knows these two data points are similar to an extent of weight 10.
So one question is that what is the actual thing that is flowing? Is it like something like the backpropagation algorithm where the derivatives are moving from one place to other, or what does this mean?
That's a good question. We didn't work out the interpretation yet. We just found a condition which asserts there has to be a certain flow. You could interpret it as the flow of this AI electricity.
Okay.
And what we're currently looking at, using probabilistic models where all these labels are random variables, and if this flow is kind of a flow of information in the sense of Shannon, of mutual information. So really this is a hard notion of information, measurable quantity.
Okay.
But at the moment we don't know what this really is, this flow.
But does it mean that you have to manually put the data in between the two sampled nodes?
No, you have to know the data, manually label the data for these sampled nodes.
Yeah.
And then you have to make sure that this data structure via the network here is such there is sufficient flow between the sampled nodes, and then you're able to learn for all the other data points the labels by solving this optimization problem. Yes, there was another question.
It's just a joke that if it's a social network, then it's a friendship that is flowing through the network.
Yeah, good point.
Nice.
That's a good inspiration for a paper.
So you're saying that, for example, in the house prices graph, basically wherever the flow goes means that there's like a dependency between the prices in the graph.
Yes. Yeah. Okay, so this addresses the question of when is machine learning possible. Second question was, how is it possible? So if there's a sufficient amount of flow, how do we turn this generated AI electricity by the labeled nodes? So for these nodes, we had an expert from Nordea which looked at the house represented by this node and found out after one hard working day that this is worth 200,000 and this is worth 600,000 euro. It's not a joke, really, in Helsinki. The prices are crazy. And given these two values, how do we infer all the other prices? And this turns out to be possible via optimization algorithms. And in particular, we apply convex optimization methods to this problem. Yeah, so these convex optimization methods essentially boil down to solving a fixed point equation. So solving a convex optimization problem amounts to finding the kind of value of the optimization variable, and the optimization variable are the labelings, so are the labels of the unknown, or the labels of the data points for which we don't know the label yet. And solving this optimization problem amounts to finding the labeling which has a zero subgradient of the objective function. And using some algebra, you can reformulate this condition, this optimality condition, as a fixed point equation. This is a very kind of widely used design pattern. So to formulate a problem or a learning problem as a fixed point equation. Such a fixed point equation is also underlying gradient descent. Well, gradient descent is a method for solving a convex optimization problem. And methods that train deep neural networks are fixed point iterations for a particular operator here. And similar, we get also here out a fixed point iteration with some operator p, which we can work out. So these fixed point iterations written down. It's not here. Okay, I missed that slide. But these fixed point iterations generate a message passing algorithm. So what we do, we spread out these labels to the neighboring nodes, which update their current belief of the true label, and then spread this updated belief further to their neighbors, and so on and so forth. So it's a message passing algorithm, what this convex optimization method is doing. And this has the advantage of being highly scalable. So whenever you can formulate a machine learning algorithm as message passing over a network, it's intrinsically scalable, because if you add more data points, then you add more nodes which have to update the messages. So it's inherent scalable. Do you know another algorithm which is a message passing algorithm over a network? PageRank? Yes. Another one?
Endgame tables in chess, for example.
Okay. Something related to deep learning. Did anybody of you hear about backpropagation? Backpropagation is nothing but a message passing algorithm over a network. In this case, in the case of backpropagation, it's a deep neural network. But again, what makes deep learning so powerful or so scalable is that it's formulated as message passing over a network. Again, this network structure comes into play quite naturally. Okay, so this answers the second question: how do we learn, or how do we solve the learning problem efficiently? We learn it by applying message passing over the, or by doing message passing over the data network. And this can be done extremely efficiently. One of my master students is implementing this for nodes, for networks which have billions of nodes. Okay. Yeah, so this condition, we worked out this condition which guarantees that machine learning is possible, this network null space property, for a chain graph. So a chain graph might represent the time series data. So each node is one time step or one time sample of a time series, and consecutive nodes tend to be similar. Consecutive time samples seem to be, or are typically correlated. And then it depends on the weights or on the amount of similarity. If, for example, I can learn a clustered labeling which consists of those two clusters. So if the connecting edge is smaller, and this is quite intuitive that this can work because this connecting edge has weight 1, all others have 2. So the edges within the same cluster have large weight, and the edge between two clusters has small weight. Whereas here it doesn't work, because you cannot distinguish the boundary between the within cluster edges. So here this network null space property does not hold. Okay, so to wrap up, we have extended this null space and compatibility conditions which we applied to answer the question of when is machine learning possible, extensions of similar conditions within compressed sensing. Compressed sensing is a main kind of thread in signal processing since the last 10 years, which is based on kind of compressing signals just by random, by introducing randomness, by randomly selecting a few pieces of the data. This is called compressed sensing, and within compressed sensing, it has been found out that there is something like a null space and a compatibility condition, which allows to tell you that these randomly selected pieces of information, like in our case, these randomly selected pieces of information are the few labels of the data points which we look at by some human expert. That this little piece of information, kind of partial information, is still sufficient, carries still sufficient information to be able to recover all labels, to recover the prices of all houses, all around Helsinki. Okay, yeah, so if you want to dig deeper, we have some recent publications on this. You can also find it on my homepage or Google Scholar profile. And yeah, I'm happy to take now questions. Thank you.
Thank you, Alex. Yeah, I think we have the time for a couple of questions at least. So go ahead.
Yeah.
So when this condition is not satisfied and you have this operator P,
Yeah.
Does the process diverge or what happens?
No, it converges but to a labeling which is nonsense, basically.
Do you have any real-world examples where you've tried it out? Like how does it work?
I have to. Maybe on my Twitter I'll find it. One of my students tried out to perform foreground extraction. So here. Yeah. So this is the result of this convex optimization method. It considers a video as a grid graph, which is evolving over time. So this is a product graph structure. At each time point we have a grid graph, and at the new time step we get a new grid graph. And the student then tried to dig out the foreground. So for a few pixels, he marked a few pixels which he knew are inside the shark. I think 10% or so. And the rest, which is marked as blue, kind of are inferred labels. So these labels, in this case, the inside is, or the label is this pixel a foreground, like the shark, or background? And if it's a foreground, it's marked blue. And this he ran on a laptop, easily, without any optimization, without any fine-tuning of compiling.
So he didn't use any like negative examples, like this is not foreground.
I'm not sure, maybe he picked a few percent also from the background.
So what is the weight between the grid nodes here?
The weight he defined by the similarity of the red, green, blue vectors. So at least you can do fancy videos with this method.
So is it like the similarity is kind of always domain specific? So you need to kind of have some domain knowledge in order to
Yes.
apply this.
Yes. Or, as I said, we also work on methods that learn these weights by looking at correlations. This is called graphical model selection.
Look up a lot of sharks and you find that they're this color.
Yeah. No, he wanted this particular shark. Only one,
Yeah.
I'm sure. Yes.
So this is binary labeling, either it's foreground or not.
No, actually what he did, he learned the label was the confidence or the probability that this pixel is foreground or background. So this is part of our new work on logistic network lasso. So he did a logistic regression for each pixel. Yeah. So maybe if you have videos, we can try out on your videos.
Is the code available online?
Not yet, I think, but I'm happy to contact you with my master student, and I'm sure he is willing to share. Well, the paper is available. It's the logistic network lasso paper, and from the pseudocode of the algorithm, this message passing rules, you write one-to-one in C or MATLAB. So it should be straightforward to implement. Okay.
Okay, thank you, Alex.
Thank you.